Good morning, my dear students. Imagine you are sitting under a huge banyan tree and suddenly a drum beats somewhere nearby. You instantly hear the sound, right? But have you ever wondered how this sound reaches your ears? Today, we will explore the very nature of sound, what it really is, and how it travels all around us. Sound is a mechanical wave. What does that mean? It means sound needs a medium to travel through, such as solids, liquids, or gases. You see, when something vibrates, it causes the tiny particles in the medium to jiggle and bump into each other, passing on the energy, just like a chain of marbles hitting one another. Array, simple. Now, here's the key difference from light or radio waves. Sound cannot travel through vacuum. Yes, if there is no air or any material, sound simply cannot move forward. That's why in space, no one can hear you scream. Also, the kind of wave sound forms is called a longitudinal wave. Picture a slinky held horizontally, moving it back and forth compresses and stretches sections in the same direction as the wave travels. So, the particles vibrate parallel to the wave motion. And about speed, did you know sound travels at approximately 343 meters per second in air at room temperature? That means in just 1 second, sound can travel more than 3 football fields. But remember, speed depends on the medium's properties. It travels fastest in solids and slowest in gases. So next time you hear a distant train, think about this fascinating journey of sound energy. Now friends, let's talk about the very source of sound, vibrations. Everything you hear, from a singing bird to a beating drum, starts with something called vibration. When an object vibrates, it causes the particles around it to oscillate as well. Think of a tuning fork. When you strike it, its two arms swing back and forth rapidly. As they move, they push the air particles nearby together, creating compressions, and pull them apart, rarefactions. This alternating squashing and stretching of air layers sends waves of pressure outward, carrying sound energy. Here's a neat little formula to remember. The speed of sound, V, equals frequency, F, multiplied by wavelength, lambda. That's V equals F lambda. Slowly now, V equals F times lambda. This tells us how fast these compressions and rarefactions travel through the medium. Also, the loudness of the sound depends on the amplitude of the vibration. Bigger swings mean louder sound. On the other hand, the pitch, whether a sound is high or low, depends on the frequency. High frequency equals high pitch and vice versa. So next time you hear a flute or a drum, remember it's all about how its vibrations are dancing in the air. Let's dive a bit deeper into the motion that creates sound waves, simple harmonic motion, or SHM. Think about someone gently pushing a swing. The movement back and forth is a perfect example of SHM. Similarly, the tiny prongs of a tuning fork move like this, producing smooth, regular vibrations. The displacement of such a particle at any time t can be described by a neat equation, x of t equals a sine of omega t. Let me say it slowly, x of t equals a sine omega t. Here, a is the maximum displacement or amplitude, showing how far the particle swings from its rest point. Omega, that's angular frequency, is given by omega equals to pi f. Again, omega equals to pi times frequency. Now, here is a fun experiment you might have seen or even done at school, the air column resonance with a tuning fork. Imagine holding a vibrating tuning fork close to the open end of a resonance tube partially filled with water. The vibrations of the fork cause the air inside the tube to start vibrating too. If we carefully adjust the length of the air column, sometimes the sound becomes much louder. This happens because the air column resonates It vibrates at the same frequency as the tuning fork, producing a louder sound through constructive interference. The fundamental resonance occurs when the tube length L equals 1/4 of the wavelength, that is, L equals lambda over 4 for tubes closed at one end. With this, we can actually calculate the wavelength if we know the speed of sound using the formula V equals F lambda. Remember, V is usually taken as the speed of sound in air, about 343 meters per second. Let's now summarize the main characteristics that define every sound wave. First is amplitude, the maximum displacement of the particle from its resting position. Greater amplitude means a louder sound. So, shout louder to increase amplitude. Next is frequency, measured in hertz or hertz. Frequency tells us how many vibrations happen in 1 second and controls the pitch you hear. A higher frequency means a higher pitch, like the shrill of a whistle. Lower frequency means a deeper sound, like a drum. Then, wavelength lambda is the distance between two consecutive compressions or rarefactions. It's linked to the wave speed by the relation V equals F lambda, speed equals frequency times wavelength. Lastly, the time period T is the reciprocal of frequency, given by T equals 1 over F. So a high-pitched sound with a high frequency has a very short time period. The vibrations happen so fast your ears detect them as a high note. Now, friends, let's crack a quick example to practice. Suppose the wavelength of a sound wave is 0.68 meters and the speed of sound is 340 meters per second. Can you find the frequency? Remember our formula, V equals F lambda, or speed equals frequency times wavelength. Rearranged, frequency F equals V divided by lambda. Putting in the numbers, F equals 340 divided by 0.68. Calculating this gives F equals 500 Hz. Shabash beta. That's a frequency well within the human hearing range from 20 to 20,000 Hz. It shows how we can quickly find key sound properties with simple formulas. Let's wrap up today's lesson with a quick recap. Sound is a mechanical wave produced by vibrating bodies and requires a medium like air or water to travel, propagating as longitudinal waves. Remember the essential formula, V equals F lambda, where speed equals frequency times wavelength. The particle displacement follows simple harmonic motion described by x of t equals a sine omega t, with omega equals to pi f, and the time period t equals 1 over f. Pitch depends on frequency, loudness on amplitude, and wave velocity depends on the medium's properties. Also, as frequency increases, wavelength decreases if speed remains constant, quite a neat relationship. Excellent friends, these are the basics that help us understand all sounds around us, from the hum of a fan to the melody of a flute. Keep these concepts strong, and you'll be ready to master waves and vibrations with confidence. Shabash!